So this is the answer to the question of how do I find that unknown exponent, right? Like if we're doing a compound interest problem and we have to say how many years or how many compounding periods does it take for the money to double, we haven't had an algebraic way to do that, right? We've had to do all this stuff graphically. But now we can use the laws of logs and use logarithms in order to solve this algebraically. So one thing to watch out for on tests is if I say algebraically determine, then you're going to have to do it this way. On the diploma, that if you want to do it using graphing, you certainly can, right? Unless it asks for things like exact values, which then forces you into an algebraic solution, because you can't really do exact values on a calculator, unless they're nice, like 2 or 6 halves, well, 9 halves or 7 halves or something would be a nice number. Okay, so let's start with a money problem. Which you are going to make. So how much money do we have right now? Give me an amount of money we have right now today we're going to put in the bank. How much? $800. Okay, so we have $800. I thought I heard 4, old ears. So we have $800 to put into a GIC. Bird strike? That was, okay, let's look up GIC rates right now. Let's see what GIC rates. GIC rates. All right, Canadian GIC rates. Close enough, right? All right, so what do we got? Let's say, not much is what we got. GIC plus. Oh, we got sleeper GICs. We got other ones. I don't know. Not much interest these days. Okay, so let's say that we get an interest rate of 1.8% per year, compounded monthly. Okay, what do we want to happen to that $800? How much do we want to end up with? Let's say triple, okay? So how long will it take for our money to triple in value? How long will it take for our money to, and I'm going to throw in something here, to at least triple in value? So how much is triple? $2,400, right? So we want to have $2,400. Now, I like to phrase it as at least $2,400 because it's unlikely we're going to hit exactly $2,400, right? Like if they pay in the compounding and all of that, you're never going to get exactly $2,400. Maybe at the end of a month we get $2,395, and then at the end of the next month it's $2,399, and then it becomes $2,401. So we want it to at least triple in value. Okay, that'll help us when we go to round our final answer, right? So let's think we have the compound interest formula, okay, which they'll give us in a question like this, all right? And that compound interest formula is A is equal to P times 1 plus I to the n. P is the principal. A is the final amount. I is the interest rate per compounding period. Okay, I'm going to abbreviate that as CP because otherwise it's too much writing, right? So it's the interest rate per compounding period, and what's N? N is the number of compounding periods, right? Which in our case, what's the compounding period for us? Monthly, right? Okay, so this is going to happen every month. Okay, so we'll go to the next page. So we want to have $2,400. We start with $800. Our interest rate was 0.018, right? 1.8% is 0.018 converted to a decimal. What am I going to do with that? It's compounded monthly. What do I do with the interest rate? Divide by 12, right? To the n. What units is n in months? Okay, so when we solve for n, we're getting months because it's the number of compounding periods. We're compounding monthly, so we need to keep that in mind, right? Because if if they had asked us how many years does it take, then we would have to convert months to years, right? Not hard to divide by 12, but just keep in mind that this thing here, right, that these change. So if I wanted years, I'd have to take that in and divide it by 12 because this is really like, if I said 5 years, we would go 5 times 12 and we'd make it 60, right? Because it'd be 60 months. But here, we don't know this. We're trying to figure that out, right? Now, up till right this very moment, if I had asked you to solve this, you would have gone in and graphed 2,400, and you would have graphed this, and you would have had to spend about 2 or 3 minutes playing with your window, right, to try and figure out, so I can see everything, okay? And then you get a solution for it, right? But now we know logs. And knowing logs allows us to solve this much easier, right? So the first step is, let's get rid of this 800. So what am I going to do with the 800? Nope. Divide by 800, right? So 3 is equal to 1, has anybody got, what's 0.018 divided by 12? We might as well just put the actual decimal in. 0.0015? 0.0015 to the n. So the 3 is the tripling, right? I want this to be triple. And it's as if now we have an amount here of 1, right? So 3 is equal to 1. That's cool. Okay, now logarithmically, again, we could have solved this graphically, right? We'd graph the 3 and then this. But what we can do is we can take the log of both sides, right? Now, log is just an operation, just like square root is an operation or squaring is an operation. So if I had said, hey, let's square both sides, okay, square both sides. Or let's square root both sides. You have Pythagorean theorem, what do? You square root both sides, right? So you can solve for c squared. What we're going to do is we're going to take the log of both sides. So we're going to say log 3 is equal to the log of 1.0015 to the n. Okay, so we're allowed to do that, right? What's a logarithm? It's an exponent. What's an exponent? It's just a number, right? In this case, it's the number that I raise the base 10 to in order to get 3. And in this case, it's the number I raise the base 10 to in order to get this, right? But we're not interested in that. We're interested in now using the law of logs, specifically the power law. So I write log 3 is equal to, and what do I do with this? Move it in front, right? So it becomes n times. So the power law, right, if you look at your formula sheet, it says log base A of capital M to the exponent n, in this case that's your capital, is n times, so it's n log 1.0015. So now we've moved the exponent out of the exponent, and it's just in place, right? So now how do we isolate n? What do we do to get n by itself? How do I get n by itself? Divide by this, right? This is n times log, and what's a log? Log, it's just a number, right? Like, don't freak out, this is log 3. Log 3 is just a number. Right? It's like, I don't know what number it is, but it's just a number. So n is equal to log 3 divided by log 1.0015. Now you get your calculator out, and you go log 3, and you hit close parenthesis, right? And then you go divided by log, and 1.0015. And if you're lazy, you don't have to close the parenthesis ever on the last bit of a calculator, because it'll do it for you. But if you like things neat and tidy, then you can close it. And what's n? 732.9. I like that. So are we going to be around to see our money triple? Is that right? Is that what other people got too? Okay. So we're going to be around to see our money triple? No, probably not. No. Oh well, wait. Yeah, that's okay. That's because what units is that in? Months. Okay. So hopefully we'll be around in 732 months. That's only like 60 years, right? So, okay, I probably won't be around. You likely will be. So, what do we say? It will take, how many months am I going to say? 733, right? Because you usually only get paid the interest at the end of the month, and this 732.9 is like almost the end of that month, but it won't quite be, so it'll take one more. So 733 months. So how many years is that for the money to triple? Or 61 years and how many months? 61 years and 1 month, I think? Yep. 61 years, 1 month. Okay, so interest rates these days just aren't really all that good, right? 1.8%, not a lot of money. It's going to take 61 years if you want your money to triple in value. So you're not going to make any money depositing it in the bank and waiting for, interest to kick in, right? Because we're just not getting very good returns interest-wise. So if you want to make money, you actually have to invest usually like in the stock market or something, or mutual funds and things that will, in companies that will go up in value. So if you find a product you like, think about buying shares in the company that makes that product. Like if you like something and your friends like something, and you know that, hey, a lot of people and your friends out of town and that, a lot of people really like this particular product, then look at the company that makes it and think about, hey, maybe I should think about investing in that company because they've got good products. Okay, but point is what? That we're solving for an unknown exponent. Now we could solve this graphically, right? We would have gone, the problem with solving this graphically is what? You have to extend that x value window out to 733, right? Or beyond, like out to 1,000. And how many steps do you think it's going to take you? Probably 5 or 6 times. Let's try 100 more. Okay, let's try 200. No, let's try 400. Let's try, finally you try 800, and there it is. Okay? This way we don't have to do all of that, right? What do? We simplified. Okay, we simplified. We take the log of both sides. We use the power law to move the exponent in front. We isolate the variable, right, by dividing both sides by this. This is just a calculator exercise, right? This is log 3, okay? And we get our answer. Okay, everybody good? So if we can solve for unknown exponents, then we can solve a compound interest problem. We can also solve a problem like this. 4 to the power of x plus 2 is equal to 75. Now we did this, right? I mean, not this exact problem, but we did problems like this when we were in the exponential unit, right? We did 4 to the x plus 2. And what did you do? y1 equals 4 to the x plus 2, y2 equals 75, and I got to, fiddle with my window until I get the thing, right? So what do we do now? We take the log of both sides. So we take log of 4 to the x plus 2 is equal to log 75. What do I do next? We move the exponent, right? So we're going to use the law of logs that says, it's one of the more useful, right? Log base a of m to the n is equal to n log base a of m. It says if you have an exponent, you just move it out front. Okay? Which then makes it something we can solve. Now, if it's a complex exponent, like x plus 2, then put it in parentheses, right? because it's that entire, so it's x plus 2 log 4 is equal to log 75. Now we have to solve for x. In order to solve for x, we have to isolate x. In order to isolate x, we're going to have to expand the left-hand side, right? Because we need to get the x by itself. We can't have this x, oh, sorry, we don't need to do that, do we? Never mind. We're just going to divide both sides by log 4. Then we'll subtract 2, make life a lot easier. So x plus 2 is equal to log 75 divided by log 4. And so x is log 75 divided by log 4, and then subtract 2, right? Because it's x plus 2. We need to get rid of that 2. We'll just subtract it off. And what's x? So work this out, right? Because you're going to make a mistake, do it now. Really, if you aren't putting brackets where you should be, or something, let's find out. So everybody come up with a number. 1.1. 1.1? Okay, round it to just give me 2 decimals. 1.11. Okay. And make sure you know the difference between tenth and hundredth. Somebody lost like 2 marks on numerical choice because they gave 2 decimal places when they should have given 1 decimal place. And unfortunately, it's wrong. Right? There's no leeway there. If it was a written response, I'd take a half mark off for rounding. Just say, you rounded, you can correct it. On the diploma, there's no leeway. If they say 10 and you give hundredth, it's wrong. You spent 5 minutes working it out, you did everything correctly, you rounding correctly, it gets marked wrong. And that's how I'm marking it too. There's no half marks. The numeric response has to be exactly what it is. Okay, so we got x is 1.11. Now, we could try that out, right? We could go 4 to the power of 3.11, right, because it's x plus 2. What's 4 to the power of 3.11? Hint, it won't be exactly 75. 74.5, right? It's going to be close. If we took the x value that we had in the calculator, right, and went 4 to the power of, and then just said second answer plus 2 in brackets, then you would get exactly 75, right? So if you put in the unrounded value, went back up to here, so once you had your x value, if you wanted to check it, you go 4 to the power of, bracket, second answer plus 2, close bracket, hit enter, you're going to get 75. Right? Because that's actually this. Right? So that's how you can solve one of those guys. Now, let's solve one of those guys that's like really ugly. We're going to do this algebraically, but on the diploma you will not have to do one of these algebraically. I will not promise on the test that you won't, but I will promise on the diploma you won't have to do this algebraically. But you may want to do it algebraically because graphically you might not be able to find an answer. Okay? And so it looks like, looks something like this. Let's say 3 to the x plus 2 is equal to 7 to the x minus 1. Okay? We've done these, right? You would have graphed y1 equals 3 to the x plus 2, y2 equals 7 to the x minus 1, and you would have found the intersection. Sometimes the problem with these is when you graph them, you just really can't figure out which graph is which, or where do they cross, or I can't see any crossing point. So I can't even answer this question graphically, right? Because I just can't adjust my calculator settings to the point where I can see what's going on. So you can fall back on, there is an algebraic solution, right? It's, I don't know, what's the word? It's tedious more than anything, right? It's a lot of work, but it's not really hard. Okay, so what are we going to do? I want to solve for an unknown exponent. I'm going to take the log of both sides. The laws of logs allow me to now move the exponent in front of the expression. But what do I have to do with it? So what's missing here? Brackets, right? Because it's not x plus 2 log 3, it's x plus 2. It's the exponent times log 3, and it's the exponent x minus 1 times log 7. Okay, here's where it gets ugly because we now have to isolate the x's. Okay, but you've done something like this. There's a similar type of solution that you would have done in trig in Math 10C. So we're just going to expand both sets of brackets, right? Just using the distributive law, saying the log 3 has to multiply the x, it also has to multiply the 2. And the log 7 has to multiply the x, it also has to multiply the negative 1. Right? Now, at any point when I'm doing this, if you're not sure what's going on, then stop and ask, hey, how did you get that line, or what's going on here? Okay, I'll wait till you're all ready so we can see the next step. Next step, x's on one side and not x's on the other. Now keep in mind, this is just a number, right? You can plug it into your calculator, 2 log 3. You wouldn't want to because it's got 100 decimals and you don't want to deal with that right now. But that's just a number, right? So, and this is just a number. So this expression really isn't any different from something like 5x plus 7 equals 4x minus 12, right? It's the same type of problem, right? It's some number times x plus some other number is equal to some, other number times x minus that same number. Okay, so I want x's on one side. I'm going to go x log 3. I'm going to move this over, and it'll become minus x log 7. Okay, so all I've done is subtract x log 7 from both sides. I'm going to go negative log 7, and I'm going to subtract 2 log 3. Okay? So far, so good? So what do? First thing, we took the log of both sides. That allowed us to move the exponents, which we make sure are in brackets in front. We expanded both sides. We moved the x's to one side. Now, I want to solve for x, so I'm going to factor an x out of this side. And the right-hand side is going to stay exactly the same. Okay, there's nothing I'm doing on the right-hand side. So we used the laws of logs, we got the exponent, we expanded, we collected our x's on one side, numbers on the other. When each expression on the left-hand side has an x, that's a common factor. I factor it out. Okay, my next step is to get the x by itself, which means I need to get rid of this by dividing. So it'll be negative log 7 minus 2 log 3 divided by log 3 minus log 7. And that's just a calculator thing, right? We're just going to put that into our calculator. Which I guess I should get out a calculator then, so I can put it in. 4.9, anybody else? Same number, different number? 4.88. Okay, so let's just try. So what am I going to do? Now, when I'm evaluating an expression like this, I put the top in brackets and I put the bottom. This long division bar here separating the numerator and the denominator says you must fully work out the top and fully work out the bottom and then do the division. So it'll look like this. Bracket negative log 7 bracket minus 2 log 3 bracket bracket. So that's the entire top in brackets, right? Divided by bracket log 3 minus log 7 bracket bracket, enter, and there we go, right? Number you guys got. 4.889820829. All right, that was the solution to something, right? What was the question? If that's the solution, what was the question? Okay, here's how I can check this, right? You could check by putting in 4.9 and expecting that the two sides are going to be about the same, but not exactly. I can do this as well. See the STO key? Store. That says take the answer. I'm going to put it into A. So I just go alpha A, right? Store the answer in A. It's really X, but A. And now what I can do is work out, give me 3 to the power of A plus 2. Enter. And I get the number. Now give me 7 to the power of A minus 1. Now what should I see? 1937.67064. Right? It's exactly the same. Okay, let's say we use 4.9. So I went 3 to the power of 4.9 plus 2. And I went 7 to the power of 4.9 minus 1. Now what do I expect to see? Well, close, but not exact, right? So you have to be willing to accept. If you're rounding, you know, the more accuracy we give, the closer these two numbers will be to each other. 4.9, not very accurate. You know, 4.89 would have been a little more accurate, and so on. Just using the actual value by storing it means that it's exact, right? You're going to get the exact value. So that's something you can do to check, right? But that's a check you kind of have to run at the time because that number's there, and you know. Or you could store it in A and just leave it and come back later and then check it, right? If you store it in your calculator, as long as you don't clear your calculator, that'll be in there for the duration of the test or whatever it is you're doing. Okay, so that's one, you know, you would use this strategy on a diploma. You would use this strategy if you really just couldn't find the window, right? If you could not find that window to figure out where the X was, you just couldn't see it, you couldn't adjust it and that, then you can do this, okay? Otherwise, use your calculator, right? Diploma exam, you don't have to show any work, nobody cares how you did it. If you can use your calculator to do it, use your calculator to do it. Okay, we've done money, we've done, I'm going to do a half-life problem. So, in 1986, there was a nuclear accident at Chernobyl. Spell Chernobyl. It contaminated the atmosphere. Contaminated the atmosphere with radioactive iodine 131. If it took $45.7 days for the level of radiation to drop from 100 units to 2 units, then determine the half-life. Half-life of radioactive iodine 131. Now, if they ask you this, they're probably going to give you the half-life formula, right? It's not on your formula sheet. Oh, wait. It's recycle day. Okay, so they're going to give us a half-life formula. I'm going to write it on the board in a sec, and then we'll figure this out. So use the formula. Formula A. Okay, mess up the formula. Okay, so in this one, A is the amount that we end with, A naught is the amount that we begin with, T is the amount of time, and H is the half-life. Okay, so ending amount, A naught is the beginning amount, T is time, H is half-life. Now time and half-life need to be in the same units, right? So if we're talking like radioactive carbon dating, then we're talking time and half-life will be in years. In this question, they're in days. Yep.
What was the very end of the question?
Was determine the half-life. So then we got this, the gist of the question is something is going, it doesn't even matter that it's radioactive or not. Something went from 100 units down to 2 units. It took 45.7 days. What's the half-life? Okay? So we just need to know what goes in where, right? This is T. This is A naught. This is, that's A naught. This is A. And this is H, right? That's what we have to figure out, okay? So we just need to put those into the formula. So we're going to say, all right, we end up with 2 units. We started with 100 units. It took 45.7 days. And there's the thing we have to find, right? That's H. Now, in any of these questions, your first step is like get rid of whatever number is sitting in front there, right? Like that 100. Get rid of the 100. So how do we get rid of the 100? Divide both sides by 100, right? So that'll give us 0.02 is equal to 1/2 to the power of 45.7 over H. And instead of 0.02, you could write that as 2 over 100 or 1 over 50, right? But it's okay. So we want to solve for an unknown exponent. What do? Take the log of both sides, right? So log 0.02 is equal to the log of 1/2 to the power of 45.7 over H. So we take the log of both sides. That now allows us to use the law of logs to move the exponent out front. So the log of 0.02 is equal to 45.7 over H times the log of 1/2. Oh, let's just write a half as 0.5. I mean, it doesn't really matter, right? Half, 0.5. Want to solve for H. How are we going to do that? Yeah, move it on the other side, right? How do we get it there? We're going to multiply both sides by H. So H times log 0.02 is equal to 45.7 times the log of 0.5. And now how do we get H by itself? Now we divide by 0.02. So, what's h? What's the half-life to the nearest tenth, let's say, of a day? Eight point 0.01? 0.9, so let's call it 8.1 days. You got a different answer? Okay, so 8.1 is correct. I think, at least according to where I got the question from, it's correct. I'm sure they've written a reasonable question, so if we Googled the half-life of radioactive iodine 131, it should come out as around 8.1 days, I would think. I would hope. You are going to see a lot of formulas with E as with E in the formula. I'm going to try and find one. Hang on, and pause. Over the last 10 years, the amount of money M in billions of dollars spent in North America by car dealerships advertising their product can be modeled by the equation. So a lot of times, any of these formulas you see, they're mathematical models for something, right? In this case, this is a model for the amount of money spent by car dealerships. The other one, it's a model for the half-life, right? You'll find all kinds of financial models. 0.15 e to the 0.3 t plus 0.78, where t is the time in years, where t is the time. After 2000. Okay, so here's this equation. It's modeling spending in billions of dollars. So if M is 1, that's 1 billion. If it's 1.5, that's 1.5 billion. T is time in years after 2000. And we want to know when does, in what year will $3 billion be spent? So in what year? Be spent. Okay, so we're using E as our base instead of, well, I mean, we've used 2 as the base, right? And we used 6 and all of that stuff. But when we took the log of both sides, we've been doing a base 10 log, right? All right, so let's plug in. Let's see what we got. We got 3 is equal to 0.15 e to the 0.3 t plus 0.78. First step, what are we going to do first? Subtract 0.78, right? Got to get rid of that 0.78. So what's that going to be? 2.22? Somebody check the math. Okay. What's the next step? Divide by 0.15, right? Okay, yeah. Question? In what year would $3 be spent? Question mark. Next time. Okay, divide by 0.15. What's 2.22 divided by 0.15? 14.8. Okay, what's next? Okay, instead of taking the log of both sides, let's take the other one, the ln of both sides, right? ln. The natural logarithm, right? So ln, and we've got an ln key on our calculator, right? So ln 14.8 calculation. Okay, so we take the ln of both sides, right? Because we have a base e. And ln 14.8, right? That's just something we can evaluate on our calculator when we need to. What am I going to do with this exponent? Just move it to the front. 0.3t ln e. What's ln e? Because we're saying, okay, remember, ln is base e log, right? So we're working out what's the log base e of e, or we're saying e to the what gives you e? The answer is 1. So this expression here, right, that's just equal to 1. So for our intents and purposes, we can get rid of it, right? So t is equal to ln 14.8 divided by 0.3, which is what? Now you just use the ln key. Get rid of it because it's 1. What? This is equal to 1. Okay, so then we divided both sides by 1 to get rid of it. It's gone. It's 1. When you multiply something by 1, it doesn't change. All right, what's 8.98? Okay, so we're going to say 9 years. Actually, no. We're not going to say 9 years. So if t's time in years after 2000, and we're adding 8 points, so in what year? 2008 or 2009? It would be 2008, right? It's like almost the end of 2008. 8.98 is like, late in December. But it's still in the year 2008, right? So if that's 8 point anything, it's 2008. If it's 9.01, it's 2009, right? But 8.99, it's still during 2008, right? So in the year 2008. So in 2008, because we're still during the 8th year, right? Hasn't clicked over to 9 yet. That's a case where we're sort of, in a sense, rounding down, right? But we're just saying it'll happen maybe December 30th in 2008, but it's going to happen in 2008. All right, I think that, one last thing. So here's the question. How do you do log base 3 of 33? What is log base 3 of 33? The question is, how do you evaluate that? We don't have any way to do that, right? I can't do base 3, right? Calculator does log, which is what base? 10, and it does ln, which is what base? E. But it doesn't do log 3. Doesn't do log 5. So here's what we're going to do. We're going to say, all right, I want to evaluate what is log 3, 33. So if I want to evaluate it, then I'm going to say, fine. then let that be x. So we want to figure out what's x. What we're going to do is we're going to take this and we're going to rewrite it in exponential form. So what is this written in exponential form? 3 to the base is 3. What's the exponent? So 3 to the x. And what do we get? 33, right? So we just changed from log form to exponential form, right? You take the base, whatever it is. In this case, it's a base 3 log. If there was nothing written under the word log, what would the base be? 10. Okay? So we say 3 to the power of x equals 33. Now, we're going to take the log of both sides. You say, what the heck do you do? Like, we just had a log, and now you're going to take the log again. So log 3 to the x equals log 33. But what base am I now using? 10, which our calculator can do. What am I going to do with this x? Move it out front and get x log 3 is equal to log 33. So what's x equal to? And what base are they? Now they're base 10, which means we can use our calculator, right? We can go log 33 divided by log 3. So in essence, we've changed from a base of 3 to a base of 10. And now we can use calculator. So what does it work out to? 3.18? This is the last formula that's on your formula sheet for logs. And it's called the base change formula. And it allows us to change from one base to another. And I'm going to write it out here. And it says the log base b of c is equal to log c over log b. Okay, so what did we do? We took log base 3 of 33 is equal to the log of 33 divided by the log of 3, right? It's the log of the base, that comes down here, this goes over there. And what base do I change to? Usually base 10, right? Because then we can evaluate that on our calculator. I could also change to base e if I wanted, right? Then I would take the ln of both sides. So instead of log, I would have used ln, and then ln. So just try this. What's ln 33 divided by ln 3? Is that trying to calculate? What? Phones are going off all over the place. What is the... All right, I don't know. What do you get? ln 33 divided by ln 3? Same number, right? It doesn't matter what base you change it to, it's always going to evaluate the same. Well, I could change it to base 5 if I want to make that a 5, right? But there's no point in doing that because I can't really solve anything. So we're going to use base change formula mostly to take a base not 10 log and change it to a base 10 log, which then we can evaluate. Okay? And it's so important that they actually give you the formula, right? And all you think of it is this. It's the log, if you change to base 10, it's the log of the argument over the log of the base. Okay? So log 33 over log 3. Say no more, right?